Good morning, everyone. I'm Dr. Mohsen Amini, and today I'm going to present about Cloud 2.0, the next generation of cloud computing systems. So first, let me briefly introduce myself. So as I say, I'm Dr. Mohsen Amini. I've received my PhD in 2012 from Melbourne University. And after that, I have been in academia the whole time. So I have been assistant and associate professor at the University of Louisiana Lafayette up to August this year. And after that, I very recently, actually less than 3 months, have moved to the University of North Texas. So I'm the director of High Performance Cloud Computing Lab, where we have currently 7 members, including 6 PhD students and 1 master's student, and of course 2 undergrad students who help us in the research. And so far we have had in total of 33 students, postdocs, and visitors within this lab. You can see some of the pictures of our groups activities together. So the last one is actually the most recent one. So our research projects have been sponsored by National Science Foundation and the state of Louisiana. At the time I was at the University of Louisiana, Lafayette. So my talk today, the outline of my talk today will include 3 parts. Firstly, I will talk about my research vision, the research mission, and the research scope of our research lab. Then I present 2, or I can say 2.5 research projects that has been conducted at our HPCC lab. Specifically, I'm going to talk about strategies to bridge the gap between machine learning and cloud systems. And another work, I'm going to talk about democratizing cloud native application development. And then, of course, I will talk about our prospective research directions and what we think will be the next big things in distributed and cloud computing systems, and of course, AI and other emerging areas. All right, so let's start with our research vision. So in our vision, we can call the past decade, let's say from 2010-ish to 2020-ish, we can call it as communication everywhere. So within that decade, basically what happened was that different generation of data networks appeared, and they got evolved, like 2G, 3G, 4G, different versions of wireless. And during this decade, people were excited with having, let's say, Wi-Fi access, free Wi-Fi access everywhere. That's why we call it communication everywhere. Basically, you have wireless access, wireless internet access, first and foremost, everywhere at your home. Prior to that, everything was Ethernet, right? So after 2010-ish, everything became more wireless. And then similarly, when you enter a supermarket, you were excited to have like a free Wi-Fi access, free internet access, and in other places, like at the university and other places. So while people were excited about that, up to like around 10 years ago, we think that the current decade is becoming more of a computing everywhere. By that, we mean that people are not excited with getting free Wi-Fi while they enter the grocery store or the university campus, but they are more excited with more smart services, like, for example, automatic checkout at the grocery store, AR, VR, augmented reality, virtual reality, features on the products that are in the store. Or for example, in the university, we may have like internal navigation and many other services like this. So that's why we call this one computing everywhere. So people generally think that computing everywhere is happening by means of what is so-called IoT devices, Internet of Things. Different types of these devices are emerging, including drones, smart cameras, smart glasses, smart watches, smart appliances, smart everything, right? Every day we see, one new smart thing, which essentially means that it has the computing ability plus the internet connection ability. While people think that these are the frontiers of the smart systems, a deeper look will tell us that these are just the facade of the computing everywhere era. Behind the scene, there is in fact multiple layers of computing systems that collectively, collaboratively providing this computing everywhere, specifically with respect to the smartness, intelligence, so collaborative intelligence. So the intelligence that we are talking about is not necessarily coming from these IoT devices. They are mostly coming from the computing tiers or tiers of computing that are generally behind the scene. So with this vision, we think that the next generation of cloud systems are emerging or will emerge in the near future. We call this new generation of cloud systems as Cloud 2.0. So let's see what are the characteristics of these new cloud systems or new generation of cloud systems. First and foremost, I guess everyone will agree that they will be AI friendly. The fact is that the current clouds, let's say we call them Cloud 1.0, have been developed orthogonal to AI systems. So AI systems have gone their own path, and cloud systems have gone their own path. So there's a gap between these two. So one of the issues that will be resolved in the next generation of cloud systems is to make it more, is to bridge this gap and making it more friendly to host AI-based applications, ML-based applications. Another dimension that we think that clouds will, the next generation of cloud systems will be, is that they will be domain specific. So current cloud systems like Amazon, like Google Cloud, like Azure, and many others, they are like general purpose, right? They sell every type of service. But we envisage that in the near future, we will have domain-specific clouds. Let's say clouds for healthcare, clouds for finance, clouds for machine learning, clouds for data analytics, cloud for HPC, and many other types of cloud systems that are domain-specific. So along with the line of being domain-specific and having like high-level APIs within that specific domain, we think that the next generation of cloud systems will be increasingly heterogeneous because we know that like at the hardware level, the ASICs, application-specific integrated circuits, are emerging. And of course, those ASICs, along with CPUs, GPUs, TPUs, all these different types of FPGAs, so they create a very heterogeneous environment. So heterogeneity is one of the main characteristics of the next generation of cloud systems. Next characteristics in our vision is that the clouds will be truly distributed. Again, the current cloud systems, that we call them Cloud 1.0, are very centralized. They are known to be centralized. They are based on the notion of data center, right? So which is very, by nature, is very centralized. We think that the next generation of cloud systems will be distributed, either vertically through edge, fog, cloud, or horizontally across clouds. So the next generation of cloud system must be prepared for this type of environment and must accommodate these type of applications that want to run in this type of environment. Next is the trustworthiness. Again, one of the problems of the current cloud systems, Cloud 1.0, is that they are hard to be trusted. So they are third party, and people are not very convenient to trust third party, services, specifically banks, healthcare institutions, governments, so they are not feeling comfortable to host their services or applications on the cloud. So we think that the next generation of cloud systems will accommodate user-based encryption and will basically embrace trustworthiness for the users. So the next characteristics of Cloud 2.0 will be ease of use. The current cloud systems actually mitigated the burden for system admins mainly. So clouds mainly help system admins in the sense that they did not need to think about maintenance anymore. They did not think about like scalability anymore. All those things are taken care of at the cloud level, mainly automatically. So, however, the current cloud systems did not favor programmers. In fact, they made the job of programmers more difficult because cloud programming, needs its own expertise. You need to be familiar with many type of services, configuring them, and many challenges. That's why cloud programming is a high-paid job, right? So we think that the next generation of cloud systems will mitigate the burden for programmers. So and make it easier for anyone, literally anyone, to program clouds. You can imagine the same way anyone can search on Google, right? Search across the internet. So anyone should be able to program cloud, right? So these are the dimensions that we think will be the next generation of cloud systems. So today I'm going to talk about, of course, we cannot talk about all these dimensions, but I'm going to talk about 2 or 3 dimensions, mainly how Cloud 2.0 can become AI friendly, how ease of use or democratized programming, what we call it, will be or can be enabled, and a little bit about how Cloud 2.0 can be distributed, or what is so-called the idea of liquid computing, as I will explain later. So with this vision about cloud systems, we define at HPCC Lab, we define our mission as to help in the development of Cloud 2.0 such that the quality of human life is improved. So we try to use this technology for the benefit of human beings. And we have done that, or we have been doing that in our projects. For example, in one of our projects that I will explain in the next slide, we try to focus on bridging the gap between AI applications and Cloud 2.0 in the context of assistive technology for disabled people. In another project that we have in our lab, we try to provide new abstractions to democratize application development in Cloud 2.0. And in another project that we have, we try to establish liquid computing across autonomous computing systems. That is, again, another feature of Cloud 2.0. And we study that in the context of disaster management, specifically in remote areas, in the middle of an ocean, or like in oil fields, in the space, you know, things like that. That's the third mission that we have defined for our lab. So based on what I explained, our research scope encompasses Cloud 2.0 programming abstractions, edge-to-cloud systems, essentially the distributed nature of Cloud 2.0, vertical and horizontal, and AI applications, basically machine learning and AI, and in the intersection of all these. So in our lab, of course, in addition to publishing papers, our goal is actually providing or creating new products, right? So that the other people in the community can make use of them. It's not just publishing papers. In fact, we try to consider publications as the result of our research, not as the goal. The goal is producing something that others can use. And all of our products are open source. You can access them in our GitHub, in our HPCC lab GitHub. So today I'm going to talk about one of our projects, which is called the Smart Site. The goal of a Smart Site is essentially to provide ambient perception for blind and visually impaired people by means of a smart glass that the blind person uses. And then the smart glass is paired with an edge device. You can imagine something like a mobile phone, a tablet, or a companion device, a laptop, or even, you know, a custom design device. And then cloud, of course, or fog. And then the collaboration between these tiers of computing will enable the disabled person to have a normal life. Essentially, the blind person will not need the white cane anymore and can have can do his or her day-to-day activities without any problem. So the idea of this project is that ML applications and systems in general, edge to cloud, Cloud 2.0, or even Cloud 1.0, have developed orthogonal to each other. So they are unaware of each other, or they have been developed in their own ways without being aware of each other. So therefore, there's a gap in between. And our goal is to basically bridge this gap. Our goal is not necessarily develop new AI methods. That's not our job. Our job is basically to make those ML applications usable across edge-to-cloud systems. So I emphasize on the word usable here because most of these applications, ML applications, already exist. However, if you deploy them on your smart glass or on your phone, they will drain the battery, you know, in, let's say, half an hour. So that's not usable. We cannot give the blind person a device a solution that drains the battery, you know, in half an hour and leave the person in the middle of nowhere. that can be even life-threatening. So we cannot do that. So it has to be usable, meaning that it has to be durable, and other features that I will talk about. So the solution that we think is that ML algorithms and system software should be designed together, should be co-designed, what is so-called ML plus sys. That is the key to the usability. And we think that if this happens, we can have a usable ML that can be deployed across edge to cloud and can provide ambient perception within real-time constraint to the blind person. So when we talk about ML visibility, usability, so let's see what are the different dimensions of this usability. So when we talk about usability, one dimension can be latency. So when we deploy an ML solution on a system, let's say on a cloud, edge, device, there are some factors that increase the latency, system factors. How can we accommodate ML applications without those latency barriers? So that affect the usability. So for example, if the blind person wants to perceive one object, if the latency is high, it won't be real time. So the inference in this case must happen within around less than 100 milliseconds. So if the latency is beyond that, it would not help the blind person. Actually, it would hurt the person, because it tells the person things that are not in the eyesight of the person anymore. Anyway, so let me move faster on other features. Another usability aspect is the resource intensiveness. So we know that ML applications are resource intensive, right? So they cannot be accommodated on small devices, on edge, or on the device. So that's a usability issue. User privacy. So the blind person, whatever the blind person sees, it will be processed on some form of cloud or edge that do not belong to the user, to the blind user. And that is the violation of privacy. So that's something that we don't want. Robustness is another feature. Accuracy is very important. Sometimes we have to compromise the accuracy of the solution, but that might be, again, life-threatening if we don't do it wisely. Scalability, so the solution should be scalable. So if you have a solution, on a server that helps the disabled people, so that, if that's not scalable, then again, it will have implications on the latency and the usability of the system, of the ML system. Durability, the energy usage. As I said, we don't want a solution that drains the battery in half an hour. That is not usable, although it works, but it's not usable. And fairness. In the system like SmartSight that I just explained, we have several ML applications that have to run concurrently and continuously on the system. So we don't want to be unfair and prioritize one application only. They have all need to be received the same service, the same level of service. So we don't want our solution be very good in one type of identification, one type of objects, but ignores others, or be very bad on others. So yeah, of course, we don't have time to explain all these. Today, I'll just focus on the intersection of ML and inference latency, ML inference latency and systems. So basically, ML inference, when we want to do it in the cloud, it will be done within what is so-called virtualization environment, virtualized environments, right? Cloud virtualization or edge virtualization. However, this virtualization itself imposes some latency that, if it is not considered, can cause latency challenges, can hurt the real-timeness of the solution. So speaking of the virtualization solutions, there are different types of virtualization solutions. First of all, we may have bare metal, which essentially doesn't have any virtualization. So the numbers here shows the number of layers. They essentially imply the overhead. So let's say the bare metal just has the host OS and the kernel, right? So the one form of virtualization is container. Bare metal is not virtualization; it's actually just bare metal, but we consider it as a benchmark for others to be compared against it. So containers are very popular these days in the cloud and distributed systems. So they have a little bit more overhead. They have a little bit more layers. We have unikernel. We have micro VMs that are unikernels are relatively new. Many of the AI applications cannot be still supported. So we just introduce them, but we don't discuss them in our evaluations. Micro VMs is another type of virtualization environment, and that are widely used on edge and on the cloud for functions specifically. Virtual machines is another type, very popular, but it has more number of layers. And a very popular one is actually the combination of containers and virtualization, that we call it VMCN, which containerized virtual machines. So they have even more number of layers. So yes, when we think about ML deployment, we should consider the virtualization overhead. Otherwise, the latency may kill the performance. The question is that how to deploy ML applications on the edge or cloud to maintain the ML usability. So let's see the decision space for this problem. First of all, when we talk about deep learning or machine learning, we need to think about inference and training. So I want to say that in this work, we exclusively think about inference because it is at the runtime, not at the training time. So we discard the training part. So even for the inference, it can be done on the CPU or on the GPU, right? And if it is on the CPU, it can be x86 type CPU or ARM CPUs. And then again, each one of these cases can be run on a container, on a virtual machine, on a micro virtual machine, on a containerized VM, or on bare metal. On the software aspect, on the application aspect, we have the inference. The software part is the inference. However, the inference can be considered as the whole thing, what we call it end-to-end inference, from the point that we receive an image up to the point that we do the detection. And but if we don't look at it as a black box and we go into that box, we'll see that there are some other components. So first, we have some pre-processing step, then we have some inference, and then finally we have some post-processing to classify and localize the decision that the object that we have detected within that picture. So now let's see what questions for the ML deployment we should answer. One question is that what type of virtualization on the cloud and edge is needed for different types of ML applications? Another question is that should we use GPU or not? Is it worthwhile to use GPUs or not? Because that's a big question. Another question is about how to configure the CPU. Should we pin the CPU or just we should use the CPU, without any pinning? basically pinning the application to certain cores within the CPU. And then the next question is that what is the impact of scale up? So basically how the overhead changes when we move to virtual machines with more number of cores, or to virtualization solutions with more number of cores. So this is the explored scenarios. We have considered cloud and edge. Here I just show the cloud. And then we have considered different forms of execution platforms. And so let me see if I can. So execution platforms. And then we use MLPerf standard benchmark applications for image classification, speech recognition, NLP, and recognition systems, recommendation systems. And then we have configured different types of CPUs, like without pinning, we call it vanilla CPU, pinned CPU, GPU plus vanilla CPU, and GPU plus pinned CPU. And then each case has been considered on different scale-up levels, like 4 cores, 8 cores, 16 cores, all the way to 64 cores. So we have done an extensive exploration across all these cases. The red line shows, for example, one of the scenarios, but we have evaluated all the scenarios. So we have used different applications. Let me skip this one in favor of the time. And then here is the summary of the results for the image classification application. On the left side, we can see only the CPU case, and on the right side, we can see CPU, GPU systems. So let's see what observation we have in this case. So first observation is that as with more number of cores, these different colors at each batch shows the different scale-up levels. So we can see that basically the scale-up generally improves when we only have CPU. It improves the end-to-end inference time. However, it is up to a certain number of cores. After that, it is flattened. As you can see, let's say between 32 and 64, there is not much improvement, which is in alignment with Amdahl's law, and that's not a surprise. Another observation that we have is that is the counterintuitive behavior of vanilla containers. So when containers are deployed without any pinning. So we noticed that in this case, the overhead is significantly high. And that's counterintuitive because people think containers as being lightweight and without so much overhead. We noticed that that is not the case. And that happens specifically when the container has a few number of cores. See, 4 cores, 8 cores, we have a huge overhead, the huge inference time. However, for 64 is like typical, like others. So we notice that this is because each container is considered as a process, and that process basically faces context switches, and the number of locations that it can go within a big CPU. Our CPUs has some 64 cores, so the number of cases are a lot, and this will impact because all the caching and all these will be impacted. That is why the overhead is so high. But once we have more number of cores assigned to each container, this overhead is reduced significantly. So we see kind of the opposite behavior in when we have GPUs. So basically, what we see is that CPU, GPU in this case is not significantly beneficial. We don't gain so much from adding GPU. The reason is that the end-to-end latency is considered. but within end-to-end latency, we have pre-processing and post-processing. The point is that the pre-processing and post-processing parts are not GPU enabled. They must be done on the CPU. So if they are significant, if they take a lot of time, if they dominate the execution time, making use of GPU will not help you much. The other odd behavior that we noticed was that in the case of GPUs, with increasing the number of cores, the inference time actually increases. That's a counterintuitive behavior. We realized that the reason is that in the situation that we have GPUs, there is a kind of a trashing situation happening because of copying data to the GPU, and the number of CPU-GPU interrupts increases, and the cache misses that happens. This will cause, in fact, having a bigger CPU along with the GPU be less productive, less efficient as having a small CPU with a GPU. So yeah, so let me skip this slide. If you want more details, this paper has got published in ICCKE conference 2022. You can read more details from there. So in the interest of time, let me be a little bit faster from this point. So yeah, I mean, in this direction of bridging the gap between ML and systems, I showed one work, which was like the impact of virtualization. But there is much more that can be done. So one of our goals is to use system knobs, system features to enable human-like cognition. This is not necessarily going deep into the AI itself, but using the system knobs. For example, how the blind person can have an attention or concentration ability like a normal person has, like a sighted person has. Like, for example, as a sighted person, we can do our activity, study, do whatever, while there is a noise around us. But if it is also our current solution, it detects the environmental noise as important as what you are concentrating on. So how can we use system knobs to implement this type of, to resolve this type of problem? Another feature that we have as a sighted person is progressive perception, which is essentially seeing an object iteratively, like in the first, or progressively, better to say. In the first iteration, you see a vague image, or just, let's say, a car. But in a second level, you see more details of that car. For example, what is the brand, what is the plate number, and so on and so forth. So how to use system knobs to implement this type of cognition. Okay, so again, this is focusing on the issue of concentration, how to implement concentration, that I have to skip. So let's go back to the main topic, which was Cloud 2.0. So we already discussed the AI friendliness. Now let's see very briefly on liquid computing. So we said that Cloud 2.0 will be truly distributed, either across edge to cloud or across clouds. So in that situation, what we need is the ability that the process can travel across these computing tiers, right? That's the idea of liquid computing. So the computing is not bound to a system. It can travel between different systems seamlessly, seamless from the user perspective. There are many use cases for this. Here, I just have one quick use case. Suppose that we have, let's say, in a coffee shop or somewhere, we have an edge server where some young people are playing games and they're using that edge server for that purpose. However, once the blind person enters that coffee shop, which is higher priority, the limited resources of that edge server must be allocated to the user, the disabled user. Then, of course, the edge doesn't have elasticity. Then the only solution to accommodate this is to seamlessly migrate that gaming service to the cloud and keep the user, continue playing uninterruptedly. And then once the blind person walks out of the coffee shop, then the service can be migrated back to the edge. So yeah, this is just one of other works that we will present it. It's published. It will be published in GlobeCom 23, and we are going to present it in a month from now. So the third dimension that I wanted to focus is actually ease of use. The visualization was not right. So the ease of use, democratized programming. So I think I'm kind of running out of time, so I should be quicker. I will try to explain this part very quickly. So, so basically, this is the idea of domain-specific serverless clouds, which again, another characteristics of cloud 2.0 is being domain-specific, therefore being easier to use. And they will be more heterogeneous, and they will be easy to program. So speaking of the ease of programming, there are already some solutions from the cloud providers to make the cloud programming easier. Essentially fast, function as a service is the common solution. However, our vision is that domain-specific serverless platforms operating across edge to cloud will be the next generation of cloud systems. So the motivation for this thought is that, let's say, the analogy, better to say, for this thought is that, let's say in a town we have something like a Walmart, right? That is a huge supermarket that sells everything, right? It's like general purpose. While we have that, and that's very useful, we have somewhere like AutoZone that just sells spare parts of the cars, or CVS, which is specifically focuses on medicines, and like PetSmart and many other more specialized vendors. So with this analogy, we think that the next generation of cloud systems, like things like Amazon, you can say, is more like general purpose. We think that the next generation will be domain specific, like, for example, clouds for HPC, clouds for machine learning, clouds for data analytics, clouds for healthcare, and so on and so forth, clouds for medical imaging, and many other use cases. And it is not just a vision. There has been actually some projects on that. Snowflake already has clouds for healthcare, clouds for finance, and so on. So what the benefits of this type of clouds is that they offer more specialized services. They offer higher programming abstractions. They can utilize ASICs more effectively, and they can provide compliance. Compliance itself is a big issue. So here we focus on the programming aspect of or programmability aspect of domain-specific systems. So to ease the programming in these systems, we have to provide new abstractions, right? So I think I mentioned these things, different types of cloud systems. And yes, by the way, I missed this point. So our vision is that with these different types of clouds emerging, the landscape of software development will be changed to a mashup of services across multiple specialized clouds. So essentially, if you want to develop a solution, you grab up some services from cloud A, some services cloud B, and just you mash them up together and create a new application quickly. So that is the landscape of software. So we are not going to start programming from scratch. Things will be much quicker. And of course, abstraction is the centerpiece to democratize and to ease programming in this environment. So speaking of the abstractions, the current abstraction that we have is called FAS, function as a service. And different vendors like Amazon, Google, Microsoft, they all provide the function abstraction. While function abstraction is good, it still doesn't provide enough abstraction for the user. It has some shortages. So the user, so AWS Lambda is the name of functions in Amazon. The user still needs to think of the data for the functions, right? Navigating data into the function and navigating the output data from the function to the storage. Also dealing with the credentials and authentication parts. So also functions are flat, right? So there's no notion of private, public, protected. These notions do not exist. Also, we lack the notion of a built-in data flow for functions. So to overcome this problem, we have proposed the notion of object as a service. So a new level of abstraction called as objects. And we inspired this idea from object-oriented programming. We call it OAS, right? So we inspired it, but that was in programming. This is in the cloud. The same way in the programming, we had functions, but then we promoted it with data, like with the notion of encapsulation and having data and functions together. So now we want to achieve that in the cloud to make it easier for people to program it. Let's say in FAS, as you can see in this figure, in FAS, in current FAS systems, the developer must provide the application logic and the state, the data. And then the FAS essentially runs the function for you, right? So what we want to achieve is that we want to encapsulate the data and functions together at the server side, at the cloud side, so that the developer just needs to think of application logic, right? So, okay, I know I'm running out of time, and then it has a lot of benefits. I'll try to be faster. It makes not only the resource management transparent, but also the data management transparent from the user perspective. So it's much easier. So it will enable public-private thing. It will have reusing in terms of inheritance and many features like that. This is the architecture that we have developed. It is called OAS. You can access it, and it is we have a working version of it. It is available in our GitHub. You can see, and it has been published in 2023 at ICCKE Cloud, so you can learn more about it there. So I try to skip that. This is the example of an object that you can code with our solution. So here we consider a video as, so basically we have the notion of class, the class called test1. The data is located on S3 storage. The name of the data is video, and it is, and then the function part, we have a public function, and the function is transcoding. And then the function, of course, doesn't have implementation in this case. It just has the container image for that function, right? So the address for the container image. So, and then we can, once we have this notion of class, we can construct objects out of it. So we can say from video one constructor, and then the object is constructed on the cloud. Then you can upload your video, and then you can call a function for your video. So this is the way, our vision about this one. Okay, I need to skip these ones. I refer you to to our paper for this purpose. So we need to implement the notion of class, like a class for video, a class for image, for this use case that we had here. And this is the experimental results that I have to skip. Just the last thing is that although this OAS is great, we still think that it is difficult to program. because our ultimate goal is that enabling anyone, literally anyone, to program cloud. This still needs expertise. This is easier than fast, but still needs some expertise, domain expertise, to be able to program cloud. So the question is that how to make the cloud programming fully democratized, like Google search, which can be done by anyone. How can we have cloud programming like that? Okay, so let's say a layman user has a query. We just do the programming for it. We cloud programming for it, not just search for that. So, for example, the user wants in a video checks the mask facing of a nurse in the video. So, how to do that? How to make that program? So, speaking of generalized. Speaking of the democratized programming, it is very similar to what we have on search engines. So if we speak of search engines, we have information search, information-based search engines like Google, that at the end of the day is all about pattern matching. So it's just matches the patterns. We have the more recent one, the knowledge-based ones, like based on generative AI, like ChatGPT, that it tells you how to detect the mask facing. So you say how to detect mask facing, and it gives you a program. So you can copy that program and execute that, right? Or you may face some bugs. But then we want to promote this to the next level, and we call it action engine. So it's not search engine anymore, it's action engine. So the idea is that the programmer, the person, comes with a query, with a high-level natural language query, and then an input file. So for this video, check the mask facing, and then we feed it to the AI engine, and then the AI engine will feed it to our OAS system. Basically, finds the relevant functions, feed it to our system. And then we do the processed video and return it to the user. So there is no search, there is action. All right. Yes, I guess I need to skip these details here. Thank you for your time. And I know I'm running a little bit out of time. But yes, I will be happy to answer any questions you may have. Thank you, and bye for now.